Chapter 4, Section 13, Rubin's Rule. As explained in the previous section, we should perform multiple imputation following these steps. In step 1, determining a single value to impute each missing data. In step 2, generate multiple imputed values based on a single imputed value. In step 3, create multiple datasets using those multiple imputed values. In step 4, perform analysis for each dataset. In step 5, average the analysis results. In step 6, integrate the uncertainty associated with the missing data imputation. We can use Rubin's rule in this step 6, pool the uncertainty. Pooling the uncertainty is a process of combining the variability of the estimates across multiple imputed datasets. In this step, we do not simply take the mean of the regression coefficients, but rather, we adjust the standard errors to consider the variability of the estimates in each imputed dataset. Since each imputation result is slightly different, pooling their uncertainty is an important step to improve the reliability of the analysis. The calculation and combination of variances are performed using Rubin's rules. Rubin's rules aggregate the estimates and their variances from multiple imputed datasets to calculate a standard error that considers the uncertainty caused by missing data. Rubin's rule is used to evaluate the uncertainty of the results of an analysis after missing data have been imputed. When missing data are imputed using multiple methods and the imputed data are then used in an analysis, the results may differ depending on which imputed dataset is used. Rubin's rule is a method for quantifying the uncertainty in the results of an analysis by considering both the variation between these different imputed datasets and the variation within the imputed datasets. Specifically, it combines the results from multiple imputed datasets and calculates the final confidence interval based on it. Rubin's rule is a method for integrating multiple imputed datasets and calculating the final estimate and its confidence interval in multiple imputation. In order to reflect the uncertainty of the missing data in the imputation, it is necessary to consider not only the average of the estimates between the imputed datasets, but also their variances. Rubin's rule considers these variances to derive a more reliable final estimate. Specifically, Rubin's rule calculates and integrates the two variances, within-imputation variance and between-imputation variance. They are the variance within the imputed dataset and the variance between the imputed datasets, respectively. Within-imputation variance is the average of the variances obtained from the analysis results for each imputed dataset. Within-imputation variance, W bar, is computed by this formula. Small m represents the number of imputed datasets. Wi is the variance computed for each imputed dataset. For example, in regression analysis, we first construct a regression model for each dataset. We then calculate the variance of the estimated regression coefficients of the model for each dataset. The variance we calculate here is the square of the standard error of the regression coefficient. Next, we take the average. The between-imputation variance expresses the variance of the estimates themselves in multiple imputed datasets. The between-imputation variance, B, is calculated using this formula. The lowercase m is the number of imputed datasets. Theta I is the estimate of the parameter in each imputed dataset. Theta bar is the average of the parameter estimates. The denominator is m minus 1 because we are calculating the unbiased variance here. When calculating variance, if the number of data points is used as the denominator as it is, there is a risk of downward estimation bias, where the value tends to be smaller than the population variance. Therefore, here, we calculate the unbiased variance by dividing by the value obtained by subtracting 1 from the number of dataset. For example, in regression analysis, first, we average the regression coefficients of the regression models of each dataset. Using this average value, the unbiased variance of the regression coefficients between the dataset is calculated. In this example, there are 3 datasets, so the denominator is 2. Finally, the within-imputation variance and the between-imputation variance are combined to calculate the total variance. We can compute the total variance using this formula. The total variance reflects the uncertainty of the final estimate. This variance is used to calculate confidence intervals and standard errors, leading to more accurate conclusions. Let's take a closer look at the formula of total variance. The between-imputation variance, B, reflects the uncertainty in the estimates between the imputed datasets. And since it is an estimated variance, it requires correction rather than direct averaging. As the number of imputed datasets increases, the reliability of individual estimates improves. Therefore, when the number of imputed datasets is large, the impact of the variance decreases. The fraction 1 divided by m represents that as the number of imputed datasets increases, the impact of the uncertainty b between the datasets decreases. Thus, this adjustment term approaches 1 as the number of imputed datasets increases. In other words, the more imputed datasets are created, the total variance approaches the sum of the within-imputation variance and the between-imputation variance. When there are fewer imputed datasets, the impact of the between-imputation variance becomes larger, and the total variance increases. In sum, this formula shows that when the number of imputed datasets is small, the total variance increases. As the number of imputed datasets increases, the variability of the multiple estimates is reduced, and the variance stabilizes. This reduces the impact of uncertainty due to missing data, and as a result, the total variance becomes smaller. It is important to know that the confidence intervals calculated using Rubin's rule do not indicate the reliability of the missing data. Rubin's rule indicates the reliability of the statistical analysis results obtained from imputed data. The imputed data contains estimates of the missing values. The estimated values themselves are necessarily accompanied by uncertainty. However, the reliability of each imputed value cannot be directly assessed. The reason is that the missing data has not been actually observed, and therefore there is no way to determine how accurate the imputed values are. On the other hand, imputed data is the raw material for statistical estimation and analysis. When performing regression analysis or estimating the mean using imputed data, the imputed values themselves are uncertain. It is possible to evaluate this uncertainty based on multiple imputed datasets. For example, when performing regression analysis using imputed datasets, different regression coefficients may be obtained based on each imputed dataset. In this case, by considering the variation between the imputed datasets, we can evaluate the reliability of the final regression coefficient, which is reflected as the confidence interval based on Rubin's rule. The confidence interval computed using Rubin's rule does not indicate the reliability of the imputed data itself, but rather the reliability of the statistical analysis results using the imputed data. The imputed data itself contains uncertainty. The Rubin's rule can be used to evaluate the uncertainty of the analysis results and quantify the trustworthiness of the results. It is difficult to directly evaluate the reliability of the imputed data itself because the missing data are not observed. However, the reliability of the analysis results using the imputed data can be evaluated using Rubin's rule. Thank you for watching. Please thumbs up and subscribe to my channel.